Alright, silly people, here's the situation. We have a golf ball that is traveling through the air. It's been hit off of the ground, pointing east at an angle theta off the ground with velocity v naught, and we're meant to find um, how far it goes, the time it takes to get there, and the equations of motion for all three directions: north, east, and um, up and down. Um, Trivially, I'm going to set the starting position to be the 0 vector. Um, and then the initial velocity in the x direction is going to be v naught cosine theta. And then in the y direction, it'll be v naught sine theta. Sure. Or no, that's in the z direction. My bad. In the z direction. It's pointing east, and x is east. There's no initial y velocity. Starting with Newton's second law, the force on the golf ball is equal to the mass of the golf ball times its acceleration. And we can split that into three directions. I'm going to call it mx dot and my2 dots, and then mz2 dots. And then you have a x direction, y direction, and z direction to the force, presumably. But not presumably, because really the only force here is gravity, which is in the z direction. So you're going to find that x2 dots is 0, y2 dots is 0, and z2 dots is minus mg. So is equal to mz2 dots. You can cancel out the m's, get minus g is equal to z2 dots. If you do a little bit of a time integral on that, you'll get minus gt plus v naught z is z dot, and then do another time integral, get minus gt squared over 2 plus v naught zt plus z naught is z, the equation of motion in the z direction. We happen to know that z naught is 0. We set it to that arbitrarily. We know that v naught z is v naught sine theta. So plugging that in, you'll have your actual answer. Okay. For y, if you do a time derivative on this, you'll get v naught y is equal to y dot, which that's also 0. Then if you do another time derivative on it, you'll get y naught is equal to y, which we also set equal to 0 arbitrarily. So all zeros for y. For x, you'll have a vx naught is equal to x dot, and a vx naught times t plus x naught is equal to x, but x naught is 0. Vx naught is v naught cosine theta, so v naught t cosine theta is equal to x. Now you have the equation of motion in three directions. To put it into a vector, you would just do vector r as a function of time, and then in vector notation, the x was v naught t cosine theta, y was 0, and this was z, so it's v naught t sine theta minus gt squared over 2. It's kind of a gross t. gt squared over 2. All right. To find how much time it takes for the ball to hit the ground again, you just set z is equal to 0 on the third equation of motion, so it's gt squared over 2 plus v naught t sine theta is equal to 0. Notice that this has a trivial solution at t equals 0, which makes sense since the ball is starting on the ground. But if we just solve this for t by moving the gt squared to the other side, and then canceling out one factor of t from each side, and then solve this guy for t, so 2v naught over g sine theta is the exact time where the ball will hit the ground again. Okay. Now you need to find out how far it goes in that time. So it's going up and down, right? So it's not moving anywhere in z. It's not moving anywhere in y. The only displacement is in the x direction. So the displacement RTF minus R0 is just the x position at the final time minus the x position at the initial time. And that was just 0 anyway. So really we just need to plug in the time that we got into the x equation of motion, which was v naught t cosine theta. So v naught times 2v naught over g sine theta cosine theta is the final x, or is the, yeah, it's the displacement. You can simplify that just a little bit. And even if you want to, you can do a double angle formula and call it sine 2 theta for the displacement. All right.